Hi, this is Janice Lee, a sales manager from Vieworks. Today's topic that I'm going to talk about is how hybrid TDI technology can benefit customers with case studies. In today's presentation, I will start off by briefly introducing the TDI technology. After that, I will go over the differences between single line scan and TDI line scan, and the differences between conventional TDI and hybrid TDI. Last but not the least, I would like to share real-world applications and case studies of TDI line scan cameras. TDI technology. Line scan cameras capture images line by line. This line is also called as a stage. A single line scan camera has a single stage. In other words, it captures the image with a single lined pixel array. A dual line scan camera has two stages, enabling it to have a twice enhanced sensitivity with clearer images. A multi-line scan camera is commonly composed of 4 stages, but the number of stages may differ from producer to producer. With more stages, it creates better images compared to prior line scan cameras. A TDI line scan camera, the most sophisticated among all line scan cameras, is composed of 128 or 256 stages. TDI stands for time-delayed integration. Time-delayed integration is essentially a line scan imaging method that increases sensitivity by oversampling the signals across a plurality of line sensors, which are synchronized in a time-delayed mode. By adding the charges from multi-line sensors, the signal-to-noise ratio is increased, producing images with sufficient contrast even at higher speeds. It performs well with a short exposure time even in low light environment. When we compare the differences between two images, we can easily see that the image taken with the TDI camera is much clearer. Then how TDI line scan works. There are 3 distinct aspects of TDI. Firstly, a target or a camera itself must move so that it can accumulate the charges. Secondly, signals are accumulated through the stages as an object proceeds. Finally, as the stages increase, sensitivity increases as well. To simply show one example of how TDI works, an image of a target first gets exposed at the very first stage and the information is stored as a chart. As the target proceeds to the second stage, charges from the first stage shift down to the second stage, accumulating the signal, making better sensitivity. After the target passing the third stage, the signal is triple times amplified and at the end of 256 stage, making signal 256 times greater. Just like the picture shown, each stage accumulates the charges down the pixel column, stacking the signals. As a result, at the bottom array of the sensor, we have almost n times higher sensitivity compared to a conventional single-line scan camera. When studying our TDI system, there are 3 must-know factors. First is an imaging speed, which is lens magnification multiplied by object speed. Second is a line rate, which can be result from dividing pixel size from imaging speed. Third is an exposure time, which is line period multiplied by number of TDI stages. Let's look at the example in the slide. An example TDI camera has 256 stages and its pixel size is 5 micrometer. It's coupled with 0.5 times lens and the object speed is 300 millimeter per second. From this information, we can calculate all three factors. Imaging speed is 0.5 times 300 millimeter per second, which is 150 millimeter per second. Line rate is 150 millimeter per second divided by 5 micrometer, which is 30 kilohertz. Exposure time is 1 divided by 30 kilohertz, which is 8.533 milliseconds. Through simple math, we can figure out required conditions for TDI implementation. Single line scan versus TDI line scan. Now we know that TDI cameras have greater sensitivity. Then why is this sensitivity so crucial? Traditional line scan sensors are composed of a single line pixel array. The sensor reads an image line by line continuously, and it is effective in an environment such as conveyor belt where object moves at a constant speed. However, there is a fatal disadvantage of a single line scan camera, which is its low sensitivity. Since the sensor captures a moving object, it receives only a small amount of light during its exposure time. Small exposure time brings about low quality images, and in an environment with fast moving objects or weak light sources, it is hard to get sufficient signals for inspections. TDI technology came out to solve the issue. With its higher sensitivity, it enables superior line rates with clear images at the same time. When we look at the sample images, it is evident that TDI shows vivid image results with steady histogram. 256 staged TDI shows 256 times higher DN with 16 times greater SNR when calculated with formula above. SNR is a root of signal. Then is TDI the best solution in every application? The answer is no. It has its own pros and cons. As explained throughout the presentation, it has multiple advantages in performances. TDI enables enhanced sensitivity. TDI also acquires higher SNR images, makes high-speed imaging possible. TDI is also effective in low-light imaging. On the flip side of the coin, it also has drawbacks. TDI is sensitive. Setting a TDI environment needs accurate alignment. It also requires sensitive synchronization of web speed with integrated stages. The technology makes constant scanning speed or an encoder a prerequisite. Its multiple stages limit the camera angle. To simply put, although the technology requires careful settings, it ensures superior performances. Then, in which applications do TDI get selected? Conventional line scan cameras are being applied in simple lens inspections where high performance is not required. Best examples will be glass, film, paper, and textile inspection applications. On the other hand, TDI is popular among most sophisticated applications that requires high sensitivity at high speeds in low light environment. Electronic products are one of the best examples. Flat panel display, PCB, COF, and ACF inspection applications utilized TDI. Air scan also can be used in those applications, but applying TDI, it is possible to capture large objects in continuous inspection procedures, and high sensitivity at high speed is achievable. As TDI shows various advantages, applications that traditionally preferred single-line scan cameras are slowly shifting to TDIs. Continuing on, I would like to explain the differences between conventional TDI line scan cameras and hybrid TDI line scan cameras. TDI is also a type of an image sensor, and it shares the structures of CMOS or CCD. CMOS sensors possess internal pixel ADCs, enabling the high-speed operation. On the other hand, CCD sensors have a single readout ADC at the bottom, displaying lower noise with better image quality. Hybrid TDI structure combines the advantages of two sensor types. Just like CCD, the sensor accumulates the charges vertically down the pixel column, minimizing the converting noise that occurs when charges are switched into voltages. At the end of each pixel column, there are ADCs so that readout can occur simultaneously at each column, boosting the speed. To summarize, hybrid TDI technology has the advantages of CMOS and CCD at the same time. Combining a light-sensitive CCD-based pixel array with the fast CMOS readout electronics, the technology ensures better sensitivity, higher dynamic range, faster speed, and lower power consumption at the same time. So we learned how hybrid TDI line scan technology and how powerful it is even in low light environment. From now on, I would like to introduce some real-world applications where TDI line scan cameras are widely used, also with case studies. As I earlier said, TDI line scan camera is popular in the electronics industry where high sensitivity and high speeds are required. Flat panel display, PCB, COF, ACF. Nowadays, the application is getting more and more diverse. Not only in electronics industry, but the camera is also becoming a good option in low light imaging. Today, we will more focus on the applications on the slide. Flat panel display is TDI's main application, so let's study more cases of it. Before we learn how TDI cameras are applied in flat panel display application, it would be better to understand the structures of LCD and OLED. Typically, the main difference between LCD and OLED is the existence of backlight unit. In LCD, the light is generated from the backlight unit and goes through RGB color filters. But in OLED, there is no backlight unit. Instead, OLED, as called as organic light emitting diode, can generate their own RGB light. There are more differences between LCD and OLED, but they still share similar layers such as polarizer, glass, and TFT. And every time when each layering process is completed, the inspection should be done to make sure there is no critical defect generated. TDI cameras can be used for detecting these defects. First of all, full ISO film of display can be inspected with TDI cameras. Let us see a test case. Application: OLED polarizer film inspection. The goal of this inspection is to detect linear defects during coating process. We had a customer who was using a quad line scan camera, but the signal was too weak. So we applied a TDI camera to maximize the signal. According to the customer's requirements, 12K TDI with a pixel size 5 micrometer was selected. The lens magnification was 0.1 times, so the pixel resolution was 50 micrometer. For light mode, diffuse reflection light was chosen. As you can see from the picture, The angle between the target and light was 60 degrees, and the camera angle was set between 50 to 70 degrees to find out the best angle to detect the defects. In this case, even though the camera was originally with 256 stages, just 64 stages were used. This is because tilted camera angle can generate blurs on the images, so the minimum number of stages were activated to reduce this blurring effect. And these are the images taken with camera angle settings set 60 degree and 70 degree. With the camera angle 60 degree, it is hard to distinguish the linear defect as the level difference is too low. But with the camera angle 60 degree, you can see the line with the naked eyes. The surrounding level of the image is 112 dn and the defect level is 106 dn. We could have 7 to 8 dn level difference, which was enough to detect the stain patterns. From the test results, we could understand that the camera angle 70 degree was the best setting option in these test conditions. On the test, the light mode diffused reflection was selected, but the light mode can vary according to the type of defect that customers want to see. This is one of the examples about how TDI cameras are used in polarizer film inspection. Next, glass. TDI cameras also can be used in bare glass inspection to detect scratches and strains on the glass. 12K TDI with 5 micrometer pixel size was selected, and the pixel resolution was 5 micrometer with lens magnification 1 times. Quicksilver light was used. And these are the images that we got from the test. We can see the scratches and strains. The quicksilver light can be a good option when we would like to seek these defects. LCD color filter. Only LCD has color filter, and it also can be inspected with TDI cameras. We also chose 12K TDI with pixel size 5 micrometer for the case. In flat panel display inspection, 12K is the highly preferred resolution. The lens magnification was 1.75 times, and accordingly the pixel resolution was 2.86 micrometer. Two different types of light were used to compare the images and their detecting performances. There are transmitted light and quicksilver light. Can you see the differences? The quicksilver light was good to see the scratches. On the other hand, the transmitted light was suitable to see the patterns. But it doesn't mean that quicksilver light is always the best answer to the scratch defects. There is no right answer for the light selection, as light mode does not exactly match to the type of defect. What we should remember is that customer is looking for the best light setting which can detect their defects clearer. Camera angle, light angle, intensity of the light are also the important factors which affect the visibility on the defects. TFT, the last part in flat panel display application. The goal of TFT panel inspection is to detect electrical defects. Higher lens magnification can be selected. In this case, it was 3.46 and the pixel resolution was 1.44 micrometer. We got the test data using transmitted light and quicksilver light. The left image was taken with the transmitted light and the right image was taken with the quicksilver light. As you can see, each image shows different information. Electrical defects and scratches can be detected if you choose the suitable light for the defects. One more test image of TFT pattern. you easily can see the short circuit. In TFT pattern inspection, generally the lens magnification is set between 3 and 5 times to have pixel resolution 1 to 1.7 micrometer. Transmitted light can be used for detecting this kind of electrical defects, but in this case, coaxial light was selected. Until now, we learned how we apply TDI line scan cameras to each manufacturing process of flat panel display. Lastly, let's briefly go over other applications. PCB inspection can be a possible application of TDI camera. This image was acquired with coaxial light. The pixel resolution 50 micrometer was enough to get defect data of PCB, so 0.1 times lens was selected. Chip-on film. The COF system inspects the circuits as well as the surface of the film, checking for defects such as scratches, strains, and foreign particles. 18K TDI with pixel size 3.5 micrometer was selected. The customer had to detect very small defects, so extremely high 5.2 times lens was required. Ring light was used for this machine. ACF bonding. TDI line scan cameras are used for checking the position and identification of conductive particles. 4K resolution with pixel size 5 micrometer was selected to get this image. ACF application requires high lens magnification to detect small particles. So 7 times microscope lens was applied instead of industrial lens, which maximum magnification is about 5 times. The last application, DNA sequencing. Simply, it is a process of reading the signals of DNA bases labeled with 4 different fluorescence dyes. The customer used area scan camera in the past, but to have the faster scanning speed with higher sensitivity, TDI has become the solution for the application. The 15 times microscope lens and green laser were used for this system. So we learned various TDI line scan camera applications. That's all I have prepared for you today. Hope you learned some new things from this presentation. If you have any questions regarding TDI line scan camera or its application, please send an email to vision@vieworks.com. Thank you for listening.